Hello, and in this statistics tutorial I wanted to introduce independent factorial ANOVA, and in particular how to do it in R. So in the previous video we talked about the one-way independent ANOVA, and that in itself is a generalization of the t-test that we talked about in another previous video. One-way independent ANOVA is a way to compare more than two groups on one independent variable. So for example, if we had 3 or 4 types of drugs and we wanted to test their effects on vigilance, we could use a one-way ANOVA. That would tell us if there was a significant difference, statistically significant difference between any of the groups. We would then do post hoc tests to follow that up and say, okay, which groups are different from which and which groups are the same. We talked about all that in a previous video, but that was with one independent variable, so testing the effects of one certain type of manipulation on a continuous dependent variable. But with ANOVA we can have multiple factors on multiple things we're categorizing people based on. So we might want to say, for example, okay, it's not just a drug that we want to compare. We also want to compare doses of the drug and say, okay, we think a certain drug's gonna affect vigilance more than another one, but the effect is going to be dependent on the dose that we give someone. So there's a larger dose is always going to be better than a smaller dose, and one drug is always going to be better than the other. But in terms of the effect size, it might be dependent on an interaction between the two factors. So a couple of terms we need to be aware of. A main effect is what we looked at in terms of a one-way ANOVA. So a main effect is saying if you look at one of the variables and collapse across the other variable, ignore the other variable, is there an effect? Is there a difference between the groups of that variable on this dependent variable? And an interaction is saying, okay, well, we know there's a main effect of one variable on the outcome, but is that effect dependent or somehow changed by a certain group in the other of the other variables? So to make this all a bit more concrete, let's take a look at our example. I've got R open here, and this is a similar example to what we did for the one-way ANOVA video. So the idea of this study is that we've given people either a happy or dull message, and we've measured their positive affect, how good they're feeling. So we're expecting obviously the happier message to make people happier and the dull message to make people less happy. But we're also saying, okay, there might be a main effect of that, but another thing we should take account for is the relevance of the message. So we'd expect it to have more of an effect if the message is high relevance. So we've got an interaction here because the two variables interact to produce different effects depending on the combination of which groups you're in. So that's the idea of an ANOVA. So how do we do the factorial ANOVA in its PSS? Now we do it using the same way we did the one-way ANOVA, but just add in our other factor. Now, one thing I should mention is we've got two grouping variables here. We've got message and relevance, but you could look at the interactions or do a factorial ANOVA with more than two dependent variables. Each of these variables has two levels or two groups within that variable. The message factor has two levels that are happy and sad, and the relevance factor has two levels that are low and high. But you can have multiple combinations of variables. So if I had a 2x6 ANOVA, for example, it would mean that my first factor had two levels, my second factor had 6 levels. But this is the simplest form of a multi-factor ANOVA, a 2x2 design. So that's what we're going to look at in this video. So how do we see if there are any main effects or any interactions? Well, we do basically the same as we did in the previous video, but just with a few generalizations. However, because we want to look at main effects and interaction effects in terms of the means, we need a different package because we want to look at the combination of these factors. I can't display descriptive statistics based on the combination of the groups. So but our ANOVA model generates that. So we need some way to get the means based on what our ANOVA model has generated. So to do that, we want to download a package called effects. So we're going to go install packages, effects, that's going to download. Now that's finished downloading, we can load it up. So library effects. Okay, so we're now ready. We've got all the prerequisites out of the way to do our ANOVA. We're going to use the same function as we use for the one-way ANOVA, the AOV function. So it's the same layout as we did for the one-way ANOVA. We need to give it a formula and our data. Now, the formula is going to be our continuous dependent variable. So in this case, what we've measured, our dependent variable, is someone's level of positive affect. And then our grouping variables are going to be on the right of the equation. So we're going to put this tilde and then put in all of our grouping variables. Now we could put in, because we've got, look up here, got message and we've got relevance, so we could put in message plus relevance and the interaction. But a quicker way we can do that is to say message times relevance. Now, because that's what we call the highest order effect in this analysis, it's the most specific effect. If we add that in, it's going to automatically add in all our main effects for us, so we don't need to specify them separately. So now we've specified what we want our ANOVA model is to be. We're just going to tell it what data we want to be performed on, and our data is called affect. I've forgotten what I called it. Oh, it's called affect.data, sorry. We also need to store this in an object so we can get summaries out of it like we did in the last video. So I'm just gonna say put that all in an object called model, and I forgot the equal sign, sorry. We're going to store that all in a model object. Now we can run a summary of our model to find out about our different effects. So this might look complicated, but it works on the same principle as the one way ANOVA. The first row tells us about the main effect of message, so whether the person got a happy or a dull message. The second tells us about the main effect of relevance, and the third tells us about the interaction between the message that someone got and the relevance it has. So we can see that all our interactions are significant. So let's start interpreting what they mean, the most important part of any analysis. So we saw that the main effect is collapsing across one, collapsing across the other factor, forgetting about the other factor. Is there a difference between the two groups? So we're saying, with the main effect of message, we're saying, forgetting about whether it has high or low personal relevance, does getting a different message make a difference to a person's levels of positive affect? And this is telling us that it does. Likewise, for the second effect, it's telling us when you have a different level of relevance, does it have a different effect on your happiness, regardless of what the message actually is. So, forgetting about whether you get a happy or a dull message, does the relevance have an effect? And again, it's telling us that it does. So, our two main effects are significant, but then most importantly, we've got an interaction effect. So that's telling us that the effect of one factor is different or is dependent on the level of the other factor. So it may be that there's only an effective message, there's only a difference between messages when it's highly relevant, or there's only a difference between the two message groups when the relevance is low, or that the difference is much bigger when a message is highly relevant versus when it's not relevant. So those are all possibilities for the interaction effect. To start kind of trying to interpret what these mean, we can use the effects package we downloaded to get some means for our different effects. So let's start off with the main effect of message. So we're going to use the effect function. So we're going to type in effect. And first of all, we want to know what the main effect of message means. So I'm just going to type in literally the name of our effect as it's written in our ANOVA table here. So I'm going to say I want to look at the main effect of message. And the next thing it wants to know is what model does that apply to? Where am I looking for the main effect of message? Well, we put our ANOVA in an object called model, so I'm just going to specify that here. And it's going to tell us, along with our means for each of the groups that are involved in our effect, do we want standard errors for them? And I do, so we're just going to say standard error equals true, and we get our means. So we can see in the happy condition, it looks like regardless of relevance, because remember that's what this main effect means. Regardless of relevance, it looks like the happy condition increased people's levels of positive affect relative to the dull condition. Now you see we get this notice here, it says message is not a high order term in the model. Now that's because when you have interaction effects, it's generally not advisable to interpret the main effects, because the interaction is telling you, okay, the effect is different. Like the main effect doesn't matter so much, because we know the effect changes as a result of this second factor. But anyway, some people like to interpret them. So we know that the main effect of message is telling us that in general a happier message resulted in a high positive effect than a dull message. Let's run the same function but for the relevance factor. And see, let's interpret our main effect of relevance. And we see that if the difference isn't as big as it is here, but there's people who have a low relevance message generally report lower levels of positive affect than a high relevance message. And again, this is the opposite way around to before. This is forgetting about what message people got, just looking at the relevance, putting all the people who got a happy message and all the people who got a sad message together and just looking at the relevance. So we can see that in general people who got a happy message felt happier than people who got a dull message, and people got a message of low relevance didn't feel as happy as people got a message of high relevance. But again, we get this message basically saying that the main effects probably aren't as important as the interaction effects, because they're affected by the interaction effects. So how do we go on and interpret this interaction effect? Well, I'm going to do a separate video on something called simple effects analysis. I've already done a video on how to do it in SPSS, but I'm going to do a video on how to do it in R2 to show you how to break this interaction effect down more, so you're not just having to look at means. But for now we can look at means to get some idea of what's going on. And again, we're going to apply the effect function, but we're going to say this time the effect we want to look at is message column relevance. And you see, if we look up here in the table, that's how R denotes the interaction effect. And we see we get our breakdown. So it looks like when the message was not very relevant, there's not a big difference between the high and the low. But when the message was relevant, there was a big difference. So it looks like our message has to be highly relevant in order for there to be an effect. But again, that's something I'm going to test statistically in the next video. But just to get an idea of the interaction effects, you can look at the cell means. Another way to depict this, and in fact what a lot of people do on SPSS, is show this in a graph, so you can see generally if your lines for your means on a graph cross at some point, that means the effect is different depending on the combination of levels, or there's an interaction effect. So that's what we're going to look at in the next video. But this was a simple guide to how to interpret a two-way ANOVA. Now, a couple more things to note. If we did, in fact, actually, let's do it. If we look at this significance value, for example, it's highly significant. But if we forgot about the interaction effect and just did a one-way ANOVA, so not even including relevance in our model, we just did, we just looked at the effect of message, for example. So this is going to collapse across the effects of relevance. So you'd expect it to have exactly the same significance level as the main effect, because that's what the interaction effect is doing. That's what the main effect is testing. But if we look at that and then run a summary of that model, we can see that our significance value is very different. That main effect was highly significant, and if we collapse across levels and just run one man over ourselves, why is it less significant? Because I told you that's what the ANOVA is doing, just forgetting about the other variables and running a one-way analysis of variance. Well, the answer to that is the way it calculates the degrees of freedom and the residuals. From the previous video, we know that from a one-way ANOVA, the size, the importance of our effect is calculated by dividing this mean squares by the error mean squares, or I call it the residual mean squares. Now, the residual mean squares is what we've not explained, or what our manipulations can't explain. It follows that generally when you add a factor, you're going to explain some more variance. So this error, the amount that's not explained, is going to get smaller. So it's easier for effects to be significant. If we look back at our original model, you can see that our effect in itself is explaining the same amount of variance, but the error the error is less. So that for the main effects, it literally is just doing a one-way ANOVA on forgetting about the other factor and just doing a one-way ANOVA just on that factor, but we will get different results because the error term is calculated differently. So that was a simple introduction to two-factor independent ANOVA. Now, this generalizes to however many factors you want to have. If we have a three-factor design, we'd get a three-way interaction, and that would be telling us that the two-way interaction, so this what we've been looking at, is different depending on what level you have the third variable. So you can go infinite with this and get 3- and 4-way interactions and stuff like that, but I just want to give you a simple example to demonstrate the concept. Anyway, in the next video we're gonna look at some graphs and look at how to interpret these interactions a bit more, so stay tuned for the next video. Thank you for watching, bye bye.